Last episode, this channel spent some quality time on a number that refuses to sit still. A piece of physics so actively contested that two separate research groups, working from two different datasets, are currently arguing in real time about which direction it's moving. That episode ended on something close to hopeful. We don't know yet, but we're getting better at measuring it, and the not knowing is itself a kind of progress. This episode is about the opposite kind of not knowing. Somewhere in the mathematics of the universe's most basic ingredient, not dark energy, not a distant galaxy, but the actual field that gives every particle in your body its mass, there may be a lower, more stable configuration of existence than the one we're currently in. If it exists, and if a random quantum event ever nudges the universe into it, the change would begin at a single point and spread outward at the speed of light in every direction, permanently rewriting the laws of physics as it went. Here's what makes this fundamentally different from every other ending this channel has covered. You would not see it coming. Not because nobody's looking. Because there is nothing to see in advance. The first evidence of it and its arrival happen at exactly the same moment, everywhere it reaches, forever. So, just to make sure we are talking about the same thing, we will start with a word physicists use in a way that doesn't match how anyone else uses it: vacuum. In everyday language, a vacuum is empty space, nothing there. In quantum field theory, the vacuum means something much more specific. The lowest energy state every field in the universe settles into everywhere simultaneously. Footnote 1. One of those fields is the Higgs field. The field, confirmed at the Large Hadron Collider in 2012, that gives fundamental particles their mass by interacting with them as they move through it. Footnote 2. Here's the mechanics that actually matter. The Higgs field has a potential energy, a mathematical landscape describing how much energy the field costs at every value it could possibly take. Right now, the field sits at a value that corresponds to a genuine minimum in that landscape, the way a marble settles at the bottom of a bowl. The question physicists have been chipping away at since the Higgs boson's discovery is whether that bowl is the lowest point available, or whether a deeper bowl exists further out on the landscape that the universe simply hasn't reached yet. Footnote 3. The honest, current answer, calculated from the Higgs boson's measured mass, about 125 GeV, known to a precision approaching 0.1%, and the top quark's measured mass, about 173 GeV, now known to roughly 0.2%, is probably yes. Footnote 4. The calculation places our universe in what's called the metastable zone, not the stable regime where our current vacuum genuinely is the lowest point available, and not the unstable regime where decay should already have happened. Metastable means exactly what it sounds like: stable enough to have lasted 13.8 billion years, without being the actual bottom of the landscape. Footnote 5. Physicist John Giudice offered the analogy that's stuck in the field ever since. Our current vacuum is like a cup balanced carefully on a table, genuinely stable under normal conditions, but not resting on the floor, which is where it would eventually end up given the right disturbance. Footnote 6. The disturbance in this case doesn't require anything external at all. Quantum mechanics guarantees that, given enough time, even a stable-seeming configuration can tunnel through an energy barrier it doesn't have the classical energy to climb over. A genuinely spontaneous, uncaused event, not a response to anything happening nearby. Footnote 7. This is why pinning down the top quark's mass to ever finer precision has become one of the more quietly consequential measurements in physics. The honest state of a real, current, unresolved question hinges on decimal points the field has spent over a decade trying to nail down. Footnote 8. Assume, for a moment, that the metastable picture is correct, and that somewhere, someday, a patch of the Higgs field tunnels into the deeper, truer minimum. Physicist Sidney Coleman worked out the mechanics of exactly this kind of event in 1977, in a paper that, at the time, wasn't specifically about our universe. It was about the general physics of any field transitioning from a false vacuum to a true one. Footnote 9. Coleman and physicist Frank de Lucia extended the calculation in 1980 to include gravity's effects, which turned out to matter enormously for how the process actually plays out. Footnote 10. Here's the sequence translated out of the equations. The tunneling event doesn't happen everywhere at once. It happens at a single point, a genuinely random quantum occurrence, forming a microscopic bubble of true vacuum inside the surrounding false vacuum. Inside that bubble, the fields settle into their new lower energy configuration, which means the Higgs field's value differs inside the bubble from outside it, which means the masses of fundamental particles differ too. Electrons, quarks, the specific values that make chemistry work at all, atoms as stable structures. All of it depends on the Higgs field holding roughly the value it currently has. Change the value, and none of it survives in a form resembling anything a physicist, let alone anyone else, would recognize. Footnote 11. If we have modeled the boundary of an expanding true vacuum bubble correctly, it does not decelerate. It does not pause to assess what it is converting. It does not, as far as I can determine, know that it is happening at all. The bubble wall doesn't stay small. Once nucleated, it expands outward in all directions at very close to the speed of light, converting ordinary vacuum into true vacuum as it goes, indefinitely, until it runs out of universe to convert. Footnote 12. This is the detail that makes you won't see it coming literally true rather than just dramatic. Nothing outruns the wall, which means no warning signal, no light, no gravitational wave, nothing can arrive anywhere in the universe before the wall itself does. The first evidence anyone anywhere could have that this occurred would be simultaneous with its arrival. There's no version of this where a telescope somewhere spots it early and sounds an alarm. And because the trigger is a genuinely random quantum event rather than a response to any observable condition, no location or moment is more or less likely than any other, no early warning signature exists to watch for, and no amount of future instrumentation changes that. This isn't a detection problem waiting on better telescopes. It's a structural feature of how the mechanism works. So, the why we're probably going to be okay? Probably. Here's the confidence grading this channel does explicitly, because the numbers in this episode deserve genuinely different levels of trust from each other. Solid, well-tested physics. The Higgs boson's mass and the top quark's mass are both measured with real precision at the Large Hadron Collider, and neither measurement is seriously disputed. Footnote 4. Genuinely contested extrapolation. Whether those measured values place the universe in the stable, metastable, or unstable regime depends on running the Standard Model's equations all the way up to the Planck scale, the energy level where gravity's quantum effects become impossible to ignore, a mathematical extrapolation roughly 17 orders of magnitude beyond anything the LHC has directly tested. Footnote 13. That extrapolation assumes no new, undiscovered physics intervenes anywhere along the way, which is a real assumption, not a measured fact. Multiple analyses through 2024 have shown the boundary between metastable and stable shifts meaningfully depending on exactly which top quark mass measurement technique gets used as input, and the uncertainty hasn't fully closed even with the LHC's most recent data. Footnote 14. It is entirely fascinating that the measurement itself is precise. The extrapolation built on top of it crosses 17 orders of magnitude this instrument has never directly tested. It would be illogical to treat those two claims with equal confidence. Now the actually reassuring number, and it's the one this section exists to deliver honestly, even in the metastable scenario, even granting every assumption that favors the more dramatic outcome, the calculated lifetime of the current vacuum vastly exceeds the current age of the universe. Footnote 5. Physicists sometimes describe this as living dangerously, which is a strange phrase for a number that, in every calculation performed so far, comes out longer than 13.8 billion years by a margin large enough to stop mattering on any timescale a person, a civilization, or a star could plausibly care about. Footnote 15. Metastable does not mean imminent. It means, specifically, not the true bottom of the landscape, but stable enough that betting against it hasn't been a mistake for anyone who's ever made that bet. One persistent public worry deserves a direct, specific answer. Could a particle accelerator trigger this deliberately? In 2008, ahead of the Large Hadron Collider's first collisions, this exact question generated real public concern. The physics answer is about as reassuring as this topic gets. Cosmic rays, naturally occurring high-energy particles from space, have been striking the Earth's atmosphere and other bodies throughout the universe at energies exceeding anything the LHC can produce, continuously for billions of years, without triggering a vacuum decay event anywhere in the observable universe. Footnote 16. If collisions at achievable energies could nucleate a true vacuum bubble, the universe has already run that experiment far more times than any human-built machine ever will. So, here is the cosmic coincidence that doesn't get enough attention. And a question that should bother you more than the bubble itself, if the metastable picture is correct. Why didn't this already happen? The early universe, during the period of cosmic inflation, briefly contained energy densities almost unimaginably higher than anything that exists now, precisely the kind of extreme conditions that should make a quantum tunneling event vastly more likely, not less. Footnote 17. Physicist J.R. Espinosa and collaborators have spent real effort on exactly this puzzle. If our vacuum truly is metastable, the early universe had the most violent, highest energy opportunity imaginable to trigger the decay, and as far as 13.8 billion years of subsequent history can tell us, declined to take it. Footnote 18. So, then if life can find a way to survive the single most energetic, chaotic, high-temperature period in the entire history of the universe completely intact, and then spends the next 13 billion years being told it might still, hypothetically, someday get unlucky. This isn't a fully solved problem. Some analyses suggest inflation's specific energy scale, and the details of how the Higgs field was coupled to gravity during that period, may have kept the field away from the danger zone by something closer to a fortunate initial condition than any protective mechanism, which is either reassuring or unsettling, depending on how you feel about the universe's early history being, in a real sense, a coin that happened to land the right way. Footnote 18. Others have proposed that some yet undiscovered physics stabilizes the field in ways the plain standard model calculation doesn't capture, which would mean the entire metastable framing is itself an artifact of an incomplete theory, not a confirmed feature of reality. Footnote 19. This channel's stated premise applies here as directly as it ever has. We are the measuring instrument, and in this case the instrument's own existence is itself a data point about the question it's trying to answer. A universe that had already decayed wouldn't have anyone left in it to calculate the odds. That's not proof the odds are good. It's a reminder that we're still here to ask the question, is doing more evidentiary work in this section than it usually gets credit for. Put this next to last episode on purpose because the two make a genuinely useful pair. The universe hasn't made up its mind was about a number, dark energy's equation of state, that we're actively getting better at measuring, where named research teams are publishing dueling interpretations in real time, and where the honest answer keeps changing shape as better data arrives. That's uncertainty of the reassuring kind, incomplete but improvable. Every year that passes leaves it a little less uncertain than the year before. This episode's uncertainty doesn't work that way structurally no matter how good instruments get. The Higgs and top quark mass measurements will keep improving. The high luminosity LHC is specifically expected to narrow exactly this question over the coming years. Footnote 20. But narrowing whether we're in the stable or metastable regime doesn't change the fact that, if we are metastable, the actual triggering event remains, by the physics' own description, a genuinely random quantum occurrence with no precursor, no buildup, and no detectable warning sign at any distance. Better telescopes help with dark energy. They cannot, in principle, help with this. That's the honest contrast this miniseries has now built across 2 consecutive entries. Some cosmic uncertainty resolves the way ordinary scientific uncertainty resolves. Better data, sharper answers, real progress you can watch happen. And some doesn't, not because the scientists aren't good enough, but because the thing itself isn't the kind of event that leaves footprints before it arrives. Here's where 2 episodes on How Does It End actually leaves you. Heat death, the big rip, the big crunch, all contested, all slow, all improvable by better measurement, all still technically open questions this channel can keep returning to as the data changes. Vacuum decay is different in kind, not just degree. Unmeasurable in advance, untriggerable by anything we could build, and, per every calculation performed so far, so unlikely on any timescale that matters that, probably fine, undersells just how comfortable those odds actually are. There's something almost funny about ending an episode this dramatic on a shrug, and that's deliberate. The honest takeaway isn't dread. It's a strange kind of comfort. The one ending with genuinely zero warning time is also, by a wide margin, the one you have the least actual reason to lie awake thinking about. There's still a lot of universe left to look at. Most of it, it turns out, isn't going anywhere without telling us first. This part, if it ever happens, was never going to tell us anything at all. It's a Tuesday.